All right, and now we move on to part two of the chi-square test, statistical significance. So what are we going to do? Well, essentially, we're going to talk primarily about theory, what statistical significance is, how we're finding it, and then exactly what we're doing when we're doing chi-square. Um, the key that you need to know about this, though, is there's really these two goals. Statistical significance is not only applicable to chi-square. We're going to see this come up over and over and over again. So if you don't get that, you might be able to do the math behind the chi-square, but statistical significance is perhaps even more important a concept to understand for moving forward in the semester. It's going to come up with correlation and t-test and ANOVA and everything we do. I'm also wanting to give you these key terms because it might be easier to just have this list of things that you need to know. So you need to know and be able to describe what's going on with statistical significance and alpha, and that's what that little this little symbol means. That's alpha, and you need to be able to describe and understand the null and alternative hypotheses. Again, this is kind of separate from just knowing how to get a chi-square test done from start to finish. So statistical significance, what is it? Well, let's say you have the following information with two groups. One of them has an average of 12 and one has a mean of 15. So is this difference real? That you can't really tell from this, right? And 12 to 15 sometimes might be important, it might not be. Maybe it happened just by chance. Maybe it was a coin flip, and the coin could flip 3 times heads in a row, or 5 times, or however many times. Doesn't mean that the coin would be unweighted, or not equally weighted, excuse me. And so for us, just because a mean of 15 is higher than a mean of 12, does that actually mean that there's a difference? Or is the difference meaningful, or is it a big difference? Basically, how you describe it is one way we're going to be using statistical significance. And as I say here, it's an attempt to clarify what it means. So statistical significance is attained. We say that there is a statistically significant difference or relationship whenever the probability of what you have seen is lower than some criteria that we have set. For example, if we say that our result would only occur about 3% of the time by chance, and we say 5% is the critical amount that we would want, then there would be statistical significance. On the other hand, if an event occurred 7% of the time, or would theoretically occur 7% of the time by chance alone, then we wouldn't say it's statistically significant because the criteria is 5%. So you set a criteria, in the case here 5%, and you see what percentage of time your statistic, your result would have occurred by chance alone. So more practically though, statistical significance tells you if there is a real relationship or difference or effect between variables. And if you ever showed this to a PhD statistics professor, they would already be yelling at me for how I'm describing this. But for us, that's where we're going to keep it right now. So it's different than that, but we're going to keep it right here. So it tells you if there's a real difference or relationship or effect or something going on, if there's something real there. But it doesn't tell you if that difference is important or if it's big. It just tells you it's not going to happen by chance X% of the time. So again, we could have two groups with the following means. We could have one that has a mean of 101 and one is 99. Is that real? Is it a big difference? What is going on? So it could be statistically significant to the point that it occurs only twice out of 1,000 times. Theoretically, given the right situations, that could be true. In that case, 2 out of 1,000 is much lower than 5 out of 100, so we would say it's statistically significant. However, is this a big difference? This is a different question. You can never say by statistical significance alone that there is a big difference. That is more qualitative, and we'll talk about that later in the semester. But for now, we can just say that the chances of it occurring are, relatively speaking, low. On the other hand, we could have the same information in a different situation, different groups, and we could find they're not statistically significant. Maybe those could happen 20 times out of 100 by chance alone. So the numbers aren't as important as the context it is in. And that's why it's so complicated. And you'll see going forward, it actually can be kind of surprisingly complicated. So the terms that we use, the terminology, is different depending on the test you're doing. So if we're doing chi-square, significance would tell you if variables in your contingency table are independent from one another, meaning the chances of one of them occurring by chance in the other variable is equal. It's just chance. Whereas when we go to t-tests, significance will tell you if two groups have statistically significantly different means on some target variable. And in correlation, it'll tell you if there's a significant linear relationship between two variables. So you're not going to use the same terminology. You have to know what your tests are doing. That's why I'm spending so much time going over the theory behind chi-square, and we'll do the same thing for t-tests and correlation going forward. So when we run statistics, we are actually testing hypotheses. We have two hypotheses we are testing when we're doing hypothesis testing, the null and the alternative hypothesis. So every test we run has both of these. And our null hypothesis, which is denoted as capital H sub 0 for the most part, states that there is no association between two variables, or there is no difference, no correlation. Whatever it is, there is no association relationship that you are probing. The alternative hypothesis, on the other hand, is that there is an association between them, or there is a difference between groups, or there is a correlation, there is something there. It's basically the null hypothesis means there's nothing going on, and the alternative hypothesis means there is something going on in a very basic sense. And when we run statistics, we're trying to figure out which one of those is more likely to be true. So let's say you could have a theory that trauma is related to depression, or it's not. Our null hypothesis is trauma is not related to depression. Our alternative hypothesis would be that trauma is related to depression. Then you do your study, and you'd see which one is more supported. This is the process of science. So really the goal of statistics, whether or not you understand this now, is questionable, but you'll see over time, the goal is to guide whether or not we are rejecting the null hypothesis. Are we going to reject it? Do we fail to reject it? And then also we want to estimate the probability of errors when we're making these decisions. So the purpose of statistical significance, and the purpose of statistics really, is to guide whether or not you reject these hypotheses and estimate the probability of errors. So what do we have to do though? We've already calculated our chi-square value. Well, the next step, and I'm going to have them outlined step by step at the end of this lecture, now we have to find the degrees of freedom, which is going to be abbreviated DF. What are degrees of freedom? They're kind of complicated. You won't really need to describe it, but if you're like me, I kind of have to understand things to feel comfortable about them. So really what it is it's the number of values in a calculation that are able to vary, that are able to change. So let's say we have a group of 20 people, and the average is 20, and we know that average is 20. Well, if the average is 20, we know that 19 of those variables could add up to be anything. They could be 380 or 8,000 or anything. The 20th value would have to be something to make your overall group have an average of 20. So in the case of 380, the last variable would have to be 20 in order for your averages to work out to be 20. If your group 19 of them had a value of 8,000, then the last value would have to be negative 7,600. And why do they have to be that way? Because we already decided, we know that the mean is 20. So if the mean is 20, the only way to get from 8,000 to for 19 to having a mean of 20 for all 20 of them is to have the last value be negative 7,600. Now, you don't necessarily have to be able to describe all of that. Really, what you need to be able to do is calculate them. And degrees of freedom are also going to be different for each test. This is important to know. Different for each test. So in chi-square, to find degrees of freedom, it is equal to the number of rows minus 1 times the number of columns minus 1. Degrees of freedom is almost always a pretty easy thing to calculate. So in our case, we have 2 columns, we have food and affection, and we have 2 rows, yes and no. So 2 minus 1 times 2 minus 1. And that equals 1. So we have 1 degree of freedom in this case. So what do we do with that knowledge that we have 1 degree of freedom? Well, now we will look to this chart. We will see in this chart we have degrees of freedom. We know we have 1 degree of freedom. Good. Well, now we have to determine alpha. I mentioned alpha earlier. We're going to have to come back and describe what it is right now. So how do we determine alpha? Well, alpha is the critical level of significance you are choosing. If you have already heard this term, then maybe you'll understand that this is also the probability of a type 1 error. We'll get back to that later. But for now, it is the level of significance chosen. And this tells us what level of error we are going to, or what level of probability, we are going to accept. And alphas will be, it can be anything from 0 to 1. And in psychology, we almost always use 0.05. And what that tells you is that 5 out of 100 times, we would expect the results that we found to be due to chance. That's what probability tells us. That 5% of the time, this result that we think is significant might just be chance. If you lower it down, though, and say an alpha of 0.01, where it's 1 time out of 100, or 0.001, where it's 1 time out of 1,000, that would be really conservative. Meaning you'd say, I never want to find something, or say that something is significant when it's not really. On the other hand, if you bumped your alpha up to 0.1, that would mean 10 times out of 100. You're going to find something that is not actually significant when you say it is significant. If you are curious about how to find it and you don't care about the theory behind it, you don't really need to know that right now. What you need to know is how we pick it. And usually it's convention. And by convention, I mean just what people do, which is 0.05. If you use 0.05, I will not ask questions about it all semester. Now, you can be more conservative and go down to 0.01 if you want, but that would only be if you really wanted to make sure there was not an even lower chance of an error, or 0.001. Those we don't do a whole lot in psychology for reasons you can ask me about if you want. So, if we know that our degrees of freedom are 1, and the probability level, the alpha, is 0.05, because we've chosen that, then we now are able to find our critical value. And our critical value we find in this chart. This is what we're looking for here. This is why we need degrees of freedom, and we need to know our alpha, or probability. So, on a test, if you're able to calculate your chi-square test, then you move on, you'll calculate degrees of freedom, and then you'll come to this chart and you'll find where the critical value is. I'll tell you what these mean in a minute. But this chart you are going to get on the test, and these numbers are the numbers. They always are the numbers. Look them up online if you don't trust me. For chi-square tests, this is what the significance numbers are. So what you have to be able to do is calculate the chi-square, calculate degrees of freedom, and find the critical value by looking in this column. If you choose to look in this column, you have to justify it to me. You have to explain it. Don't do that. So in our example, we saw that there were 2 rows and 2 columns, so we have 1 degree of freedom. It means the critical value is 3.84. So now we come to our decision. What do we do about our hypotheses? Well, we have our null and alternative hypotheses. I've written them out on here. The null hypothesis is that the observed is equal to the expected. There is no difference. And our alternative is that the observed is not equal to expected, basically, that there is some association between them. You could also say that training and danceability are unrelated, or they are related. There are multiple ways that you can word the null and alternative hypotheses. If you go with these for chi-square, that's good for me. Now, the key thing you need to know about chi-square value and the critical chi-square value is the relationship between the two. So if the chi-square value you calculate by hand is larger than the critical one from this chart, then the observed frequencies are significantly different than expected, meaning there is an association. So if your chi-squared is bigger than your critical chi-square value, there is a significant difference. Or, I'm sorry, I didn't mean to say difference. A significant association between them. They are related, the two variables. So in our earlier example, we had a chi-square value of 25.36. And on the last slide, we saw that the critical value was 3.84. Because 25.36 is greater than 3.84, excuse me, we then reject the null hypothesis. We say that they are associated. If this value, this 25.36, was, let's say, 1, then we would fail to reject the null. We would reject the alternative hypothesis. But in this case, our chi-square value is big enough that we are pretty sure, at least 95% sure, that the values are happening not by chance alone. All right, so what are the steps to this process? I told you I'd outline them, and this is really what you need to know in order to finish a complete chi-square test. You need to first make your contingency table, then calculate your chi-square value. You have to first calculate the expected values, and then you can calculate your chi-square. Then you need to calculate degrees of freedom, which will be relatively simple. Then you'll need to determine your significance value. It's going to be 0.05 unless you do something weird. Then you'll find the critical value in the chart using 0.05 as your significance level. And then determine which hypotheses to reject based on if the critical value is lower than the obtained chi-square value. All right, so right now, this is what I think we're going to be working on in class. If you have questions, please bring them. We'll watch this again, but we'll walk through each of the steps and I'll explain them in more detail if you need them. If not, then good, but still come and work through some practice problems. I also will have a practice problem through this similar setup with PowerPoint, and then a couple of them I did by hand online, so please check those out.